Hello guys, welcome. Today I'm going to talk about an interesting part of the exhaust arm project that I didn't really highlight in the last video. Today I'm going to talk about the design of the electromyogram that's on the exhaust arm. You see, in the human body, we have a lot of signals. Signal coming from our muscles, signals coming from our heart, from our brain, even from the movement of our eyes. All those things creates a very, very low power electricity. And as you can see here, for what will make the difference between one part of the body and another is going to be the frequency range. So as you can see here, the electromyogram, it's from 0 to 500 hertz. And now that's the really wide range, but the usable energy is within 50 and 150 hertz. That's where you can have the most of the energy coming from the of your muscles. That's where you have the peak values. And if you want to retrieve the electricity coming from your brain, whether it's an alpha, beta, or gamma wave, those are also different frequencies. From the heart, it's a different frequency. Now, technically, the heart is also, the myocard is the part of the heart that makes our heart beat. And myo means, the muscle, and card is the heart. So myocard is the muscular tissue of our heart that allows it to beat. And I don't know if you ever had an ECG, but even in the movies, you see the electrocardiogram beeping, beep, beep, beep. And when they are losing the patient, what they do with the defibrillator is they're using, once again, electricity to get the heart going again. And yeah, as I said, what will make the difference between one signal and another is going to be filtering. Now, it's true that you have, for an EEG, for example, signals that are just crossing or superposed to each other, especially with the EEG, which is really, really difficult to process. Hardware filtering for an EEG is not enough. You need to also include a lot of digital signal processing through digital filters. But here we're just sticking to the electromyogram, which in some sense is quite, it's easier to manage than the EEG, for example. And as you can see here, the electricity in our body is not continuous. We have it's not DC. We pretty much have some AC current. You can see here with the peak frequencies, the way it looks, it's an alternative current that we have flowing through our body. That's mainly because of the ions. The ions are what creates the difference in potential in our nervous system that's carrying the information, or the signal that flows through our body. So here I'm using LTSpice for my simulations and everything. And here is the very, very basic design, the most important part of my EMG. But there's still a lot of other parts that are on my EMG. This is just to make the simulation run a little fast, because the more things I put here, the longer it will take to plot the signals. And yeah, it's a little ugly here because I am using the spice models of the op-amps I actually use on my project. And one of the reason is whenever you're simulating something, you want to have the most reliable data, because there's no point using something that's just going to give you wrong values, especially in my case. For somebody who's broke like me who cannot afford an oscilloscope, I rely heavily on the ADC of my microcontrollers to observe the signals. And at the same time, I also need to rely a lot on the simulations to, give me an idea. And it's also very, very important before buying a component to have a clear simulation. That's why you'll see for most electronic IC devices, you have the SPICE model, which is available for free for this particular reason, that allows you to somewhat know the behavior of the component before buying it. Maybe it won't actually suit your need. Sure, you have the data sheet, but you also have that. And I think it's a really, really solid tool to use whenever you can. So here is the kernel, if we can say, of my EMJ. This is the equivalent schematic. So these things are is pretty much the same thing as here. This is the more conventional way of representing op amps, but this and that are the same, just that here I'm using the importing the library, the SPICE model of the component. And I'm going to show you how to do it in a few seconds. So this is how you can use the SPICE model of any component. I mean, I'm saying any component, but sadly you will not find a SPICE model for everything. And well, so right here, let me just specify this. If I want a model of the LM741, I just ask Google. So what do we have here? I like to go on, for example, I know the LM741 is from Texas Instruments. So I like to go on the website of Texas Instruments to get it there. You don't want to take your SPICE model from anywhere. So yeah, here I just download the file. It's downloaded, and I'll just take it and place it. You can put it anywhere, but I just want to put it here since this is the folder related to the video I'm making, just to put everything in the same place. So right here is a model. I'm gonna extract. Where is it? Okay, so here I have extracted the model, and we will open this with the .lib file. We're gonna open it with LTSpice. So here is the description of the behavior of the component. And you come here, you're gonna look for that dot sub, I don't know what that is, sub CKT LM741, non-inverting input, inverting input. So this is the definition of all the pins that you'll find on the device. But just look at this. That's where you click here and you easily just say create symbol. Do you wish to automatically create a symbol? Just say yes, there's no big deal. So here you have your .lib file, and okay, so this numbers corresponds to the different the non-inverting input, the inverting input, all this negative input. So here you can just rename them. Oh no, we said one was the first one was a non-inverting input. So oh, my bad. So where are we again? Here. So you can just call it in minus, in plus, and you can even move it. And of course you can change pretty much everything here, and you just save it. You can say yes, and the cool thing is now you're gonna have that in your libraries in auto-generated. Okay, this is an old file, so what I'm gonna do is I'm just gonna close this one, and I'm gonna reopen my model, and here you have it, the LM 7741. As I've made it now, I can change the names and do whatever I want. So I can have U1, U2, U3, and by using that, I have the actual, the closest to reality as possible. Now let's go back to our filters. As you can see here, I have a high pass, first order high pass filter with a cutoff frequency of 0.8 Hertz. I placed this one here just to remove the DC component of the any DC component that's on my body, because when you have offset and amplification, they don't mix well together. You really quickly get to saturation, and you don't want that. So with this, I'm just making sure that I remove any DC component from my body. And okay, you know what, I'll actually explain with the other schematic because this one is a little confusing. So it's pretty much the same thing. And yeah, by the way, this is the instrumentation amplifier, which is equivalent to having those three. And here's the data sheet of the AD620. As you can see, let me zoom in a little bit. Here you have it, the instrumentation amplifier circuit made up of 3 different op-amps. Everything is condensed into this one single amplifier. The great advantage of this is it's more compact. So instead of having 3 or sometimes even 2 IC components on your PCB, you'll just end up having one. Here it looks bigger than this, but in reality, it's as they have the same size. You can definitely use, I would recommend precision amplifiers, and by using this, you also have good results. Because, I mean, instrumentation amplifiers are a little bit, I mean, not just a little bit, they are definitely way more expensive than regular op amps. And it makes sense in a way. So, as I said, here I have a high pass filter just to remove the DC offset. Here is the gain of my amplifier. I have multiple stages of amplification because I've read that when you have, especially for this kind of really sensitive small signals, you don't want to over amplify it right from the beginning. You rather break it down into multiple stages and keep the first stages as small as possible. So here I'm using, let's go back to here, I'm using a 1K resistor, and if we look at the datasheet, of the 8620, we can see that with a resistor of 1K, I am at 50. I have a gain of 50. So here's the times 50 here. Here I have the, I'm looking for a bandwidth, if you remember, 50 to 150 hertz. So now having a bandwidth that's exactly at the cutoff frequency, and especially since I have a second order, here you see I have two capacitors. So if I'm at the cutoff frequency, the signal is already strongly attenuated. So you don't want to be exactly at the cutoff frequency. If you want, a high pass filter like this one at 50, you want to start at probably 40 or 30 hertz. And yeah, so here are the values of my, I just cascaded this first order, the same values here. You have, when it comes to active filters, you can choose whatever you want. You have the silent key, Butterworth, all those things. I tried different kinds, and as far as I can remember, I had the same results using a silent key bandpass filter and using, just by cascading my first order filters here. So I just stick to this, but I may change it on the final design, but it has been working quite well. So well, I'll see if I'm going to change it or not, but I don't think so. So here you have the second order, the high pass filter, 32 hertz. Here you have 1K and 100K. So here we have an inverting amplifier with a gain of 1K, 100K. So we have a gain of 100. And here we have a low pass filter with a frequency of 160 hertz. So we have an overall gain of 5,000. But since we are using filters and second order filters, we have a second order bandpass filter here, you will see that the gain is not even close to 5,000. Not even, you're going to see how small the gain is compared to the values that we have because of the filtering. So here I have a AC sweep analysis, which will give us the frequency response of the system, the baud plot, because using it in a transient analysis is just not it's not useful here because it's really all about analyzing how it behaves at any given frequency. So right now I'm gonna launch the simulation. And okay, we're not really gonna use this one anymore, so I can just close it. And here we can analyze. I don't need to look at the phase, so I'm just gonna stick with this, the magnitude. So as I said, we are nowhere close to 5,000. As you can see here, our peak magnitude is around, let's say, 40 decibel. And we are in decibel per decade, so we are at roughly 40 decibel per decade. And to calculate the gain here, we are at, okay, something that I forgot to mention. As you can see here, we have it's a differential op-amp. So I'm just assuming that, I mean, it's just something that I took conventionally like that. I made sure that I had a difference, like 2 minus 1 will give me a unity gain here. It does not necessarily mean that when you're contracting your muscle, the voltage, the potential will, the strongest potential will become, because when you're not contracting your muscle, normally you're at the same potential, so you have 0 volts. And when you're contracting your muscles, you're going to create a difference in potential. And I don't really know what's going to be the value of that. Is it a 50% increase? In that case, instead of having 2 here, I'll just put 1.5. Is it 100%? Is it 10 times stronger? Honestly, I don't know. But just to have a unity gain here, just to start with, 0 dB having just 1, something classic. I just put 2 on the positive and 1 on the negative. So 2 minus 1, I'm going to have 1. That's also, just to simplify things a little bit here and look how it behaves. So here we can see that, as I said, we are at roughly 40 decibel. So if you want to calculate the gain here, it's going to be, it's 20 times log of whatever the value of the gain is equals to this value, which is 40. So if you want to have the value of the gain, what you'll do, let me, probably, let me see if I can open a little file here, just so that we can visualize. So I said 20 log of the gain equals 40. So we're going to have log of the gain equals to 2. So if you want to gain, the gain is going to be equals to 10 to the power, how can I represent that? 10 to the power of 2, which is 100. And this is our maximum value. And the value, oh, it froze. Yeah, when you come out from the simulation, and it usually makes the software crash. Here we are. I'm going to make sure to not come out from this page anymore. So as we've seen, we had a pretty much just an increase of 100. But here we have an overall gain of 5,000. And we're not seeing the 5,000, we're seeing 100. Now, if I change the frequency here, let's say I'm gonna, because we've seen it goes to 150. So for example, here I'm at 275. I still have a really strong magnitude here, which is unnecessary, really, because we don't need to go that far. So, but what if I decide to make the low pass a little smaller? You know, I can put it at, if I use change the value here, instead of having 10K, I put 20K. So I'm dividing this value by 2. It's going to be, instead of 160, we're going to be at 80 hertz. And you're going to see how it's going to change. It's a slight change, but I mean, at least here at 200, and we are having the the magnitude is slightly lower, and then by making it even, we can even go even more low. We can go lower than this one. Now the thing is, it is also affecting the peak value of the gain. Our maximum was 38, and now our maximum is 32. So 32 at 100 hertz. So I don't necessarily want to sacrifice any gain. I don't want to lose, because that we have a loss of around 6 dB, and 6 dB is a lot. Is a lot of amplification that we've lost. And since we are acquiring really small signals, it's a good thing to have a gain that's quite, a little low, a little high. Excuse me. So for this reason, I really want to stick to this, having at least, you know, um, 100 times the signal that I have in input and the input. So I'd rather leave it like that. And I've tested it and it works, but this is not, the final design or even the complete design. It's just the way, I split the video in two for this reason. I don't want to make it too complex. I want it to stay digestible. So as you can see here, and I can also do that, modify the values of this filter. And that's the reason why having the SPICE model of the op-amps you're using is really important, because it gives you something that's close enough to reality, and you can make all kind of analysis and test different things. And afterwards you go to experimentation part, and then you say, okay, you're gonna finalize your thing and make a PCB out of it and everything. So it's a long process. It's a lot of fine tuning, but it's fun. It's fun. Here we're gonna have a little look at the slope of filters. So here's a decade from 1 to 10, from 10 to 100, 100 to every 10 times 10 is a decade. So here I place my cursor here. As you can see, we are at 40 dB, which corresponds to a second order filter. But in this decade here, it's a little bumpy. We're not at 100 dB anymore. We are at pretty much 20. It becomes a little bit like a first order filter here. And that's because there is an interaction created by the low pass filter. So the low pass filter has an effect on the high pass and vice versa. So it's not you will not get a slope that's really, I mean, you can, if you lower the low pass filter, the slope is going to be a little, you know, it's going to be a little more flat here like this, and you have a lower gain. And again, you have a lower gain. So you need to probably amplify it even more. Is that necessarily, is that a necessity? And you have all these things that you have to take into consideration, and at some point you have to stop simulating things and start testing it and see what it looks like. If the result you have is satisfying, you can stick to it and say, okay, I'm going to keep it like that. But it's a good thing to start from the simulation. So right here, we've seen how the influence of the low pass and the high pass filter, how to import a SPICE model of a given device. So right now I'm going to stop with the simulation here. I tried to edit the video to make it as short as possible, but it's still quite long. I really wanted to show you the simulation and the experimental part in the same video, but the video is already quite long. I don't really want the videos to be too long. So we're going to keep that for a part 2. See you soon, and stay tuned. Bye.